Safety during collisions is all about reducing the force on objects colliding. A common example of this is crumple zones in cars. When a car collides with something, there are parts of the car designed to crumple up. These are the crumple zones. But why do they work? By changing shape, the crumple zones make the time over which the impact occurs longer. A longer impact time reduces the force on the objects involved. This includes the passengers, and less force means less injury. So what's the physics? Well, think back to Newton's second law, F equals ma, and the definition of acceleration. Acceleration is the change in velocity divided by the change in time. If we substitute the acceleration equation into F equals ma, by replacing a with change in velocity divided by change in time, then we get force equal to the mass multiplied by the change in velocity divided by the change in time during the impact. Now look, the top of the right hand side of the equation is a mass multiplied by a change in velocity. Essentially, this is a momentum, a change in momentum. This means that the impact force is equal to the rate of change in momentum. We can also rearrange to give force times change in time is equal to change in momentum. I'm going to stop there for a second to talk about Newton's third law in collisions. This is the one that is usually described as, for every action there is an equal and opposite reaction. But what it means is that forces occur in pairs that are equal size and in the opposite direction to each other, like the forces on bodies colliding. Here, the size of the force on each car is the same, and they're in opposite directions. As their impact time will be the same as they are colliding with each other, and the forces applied are the same size, the result is that the change in momentum for each car is the same size, but in the opposite direction. One will gain momentum, and the other will lose it. If the yellow car gains 100 kg-meters per second, then the green car will lose 100 kg-meters per second, which is consistent with conservation of momentum that we learnt about in our last video. Because the total change in momentum for both cars will be zero. The change in momentum for one car cancels out the other. Right, back to the equation. This rearrangement is often called the impulse equation, as force multiplied by change in time is a quantity called impulse, measured in Newton seconds. Knowing that force times change in time is called impulse is on some GCSEs but not others. Please check your spec. So how does this equation explain why making impact time longer makes forces smaller? Well, during most impacts that require safety measures to be put in place, the change in momentum is fixed. Usually the body concerned will be travelling at a certain speed, hit something and stop. So the change in momentum is fixed, but is equal to the force multiplied by their impact time. If we make the impact time longer, then we have to multiply it by a smaller force to give the same change in momentum. And this is why it works. When you're explaining safety features, you need to make sure you make these points. Number one, a material or part of the object colliding is squashed during the impact. Second, this increases the impact time. Third, which reduces the rate of change of momentum. Don't just say momentum here, you have to say rate of change of momentum. And then finally, therefore, reducing the impact force. If you say all four of those things, you will have covered all the physics that links the increase in impact time to the reduction in force. If you're enjoying this so far, please give me a like, subscribe and hit the bell to be notified of future videos. Got a question or an idea for a future video, something you want to know about? Write it in the comments. There are lots of real-life applications of this piece of physics. Safety helmets for cycling and motorcycling have a thick layer under the outer shell which is designed to squash on impact. This increases the time taken for the head to stop on impact, reducing the rate of change of momentum, therefore reducing the force to the head and the injury sustained. It is important to replace helmets if you drop them or have a crash in them, as the safety layer doesn't bounce back. So once it's been squashed, it becomes less effective because it can't squash as much next time. Airbags increase the time taken for a person's head and chest to stop during a collision. Again, this reduces the rate of change of momentum, which reduces the force on the head and chest, therefore reducing injury. Seatbelts do exactly the same job again. They increase the time taken for a person to stop by stretching as the person's body is thrown forwards into the seatbelt. This reduces the rate of change of momentum and therefore decreases the force and the injury. In the UK, it's the law that babies and young children must travel in car seats until they are 1.35 metres tall or 12 years old. These seats have lots of extra cushioning to reduce the force of an impact. For very young children, the seats must be fitted facing the rear of the car, so in the event of a head-on collision, the child is thrown into all the padding on the back of the seat, which increases the time they take to stop, reducing the rate of change of momentum and the force, and also spreading the force over the whole of the child's back and legs. This reduces the chance of injury significantly. Finally, we've all been on a playground at some point in our childhoods. You may have noticed that the surfaces in playgrounds under the play equipment are squashy. Now, the reason for that is to increase the time it takes for a child's body to stop if they fall. Again, reducing the rate of change of momentum and therefore the force on the child, and reducing the chances of the child being injured. In my next video, I'll be showing you how to do some calculation questions using the impulse equation. Remember to like, subscribe and hit the bell if you want to be notified of future videos, and check out my other videos on forces. See you next time.